In February 2011, a computer program that we named Watson after the founder of our company made history by beating the two world champions in a game called Jeopardy. It was the first time that a computer had competed in a word game at a level with humans. And I was privileged to be in the taping room that day. I was in a role where I was overseeing a lot of the research we do worldwide, the very scientific work. And I can tell you none of us knew what was going to be the outcome of that match. Watson had lost some practice rounds, that had won one or two. The team were nervous wrecks. We had no idea what was going to happen. But when it did win, we knew something had changed fundamentally, and we knew we were at the dawn of a new era of computing, which we've been calling the cognitive era of computing. So I'm going to mostly in this talk look forward and show you some of the places that we think we're going. You've already heard a few from our conference chair. But I'm going to focus more on the software and the language sides of the house, perception sides of the house. But let's start with a little bit of a look back at the eras of computing. Back before probably anybody in this room was born, or at least most of us, was something we call the tabulating systems era. These were not very intelligent systems. Abacus was a tabulating system. Then we got some machines that kind of mechanically helped you do things. Most of us, however, were born into what we call the programmable systems era, and that's where we have been ever since, where in this era you wrote code, basically. You wrote instructions to the computer, and the computer followed the instructions. What's changed over time is the computers have gotten much, much smaller. They've gotten much, much faster. They can carry out much more complex instructions. We've got layers of software on top that make them much easier to talk to. But we're still programming systems at the bottom. In this cognitive systems era, the reason we're giving it a new name is because we feel that we are making a fundamental change here from systems that you tell what to do to systems that you teach, systems that learn, and from that knowledge then can take action. So that's kind of the way we've been thinking about these eras of computing. Why do we say cognitive? That's basically just an analogy with what the human model is. As we perceive things, we have our 5 or 6, if you like, ESP senses that help us understand what's going on in the world. We have memories. We can save information in. We can learn concepts. We have the ability to reason about those concepts and take them forward. We use that reasoning capability to solve problems, and then we can act on those problems, sometimes by physical motion, wandering around a stage, or sometimes by our words and the signals that we produce and so on. Just so a cognitive system will have all of those types of capabilities. Its senses, the way it perceives, may be different than ours. It may have sonar and radar in place of vision, or maybe it'll have all three. They have, for a long time, computer systems have had memory. They are getting the ability to learn concepts, and that's what's really exciting about this era, is the ability to teach them concepts and have them be able, again, to reason and to solve problems using those concepts. And they have had the ability to act for some time. We have robots, we have cars that can move, but again, we have for a long time had systems that could send an email or an alert or a signal so that action got taken by humans. So when we talk about cognitive systems, we are thinking of systems that eventually will embody all of these traits and may go a step further, may actually have a sense of identity of their own in the future. Just as you know who you are as a person, these systems may stop being just route numbers and have a sense of themselves. Okay, does that mean, and there's been a lot of press about this lately, that computers are going to be displacing all of us anytime soon? We don't think so, and it's not the model that we are working towards, frankly. We look at, for all those similarities between humans and systems, we see some fundamental differences that aren't going to be bridged anytime soon. Machines have been better than we are for a long time at doing really fast math. There are very few people in the world that can compete with the speed of a large-scale processor. Computers can track very complex things. They can have statistics sort of built into them, whereas humans kind of aren't so good at statistics, at least most of us, as a way of reasoning. On the other hand, humans have some very separate characteristics that, frankly, I don't know if they will ever be given to systems. I hate to say that because we've been proven wrong for generation after generation as things advance, but they're certainly a long ways out there. The ability to be self-directed, to set goals and understand where you want to get to with your life, if you will, that is a uniquely sort of human thing. Common sense is something we have tried for years to teach computer systems, and it turns out not to be a very easy thing to give somebody. It takes a lot of background. The ability to have values and make value judgments is another of those traits that kind of distinguish us from anything that we're capable of at the moment in the sphere of machines. Both sides are very good at pattern matching, but in very different ways and possibly complementary. And so the hypothesis that we have as we're doing research in this space is that the machine will come to be a strong partner to humans. And the types of advances we're trying to make are to help people to move better in the world, to be able to make better, faster decisions. Do we have any Star Trek Next Generation fans in the audience? Got a couple. Okay, so some of you may remember Lieutenant Commander Data. He was, for those of you who are not Star Trek fans, he was the android officer on the starship. He was very much a helper to the humans. He did not replace them. The men and women of the fleet were still there. But he had an incredible bank of knowledge and the ability to reason and to work together with the humans to solve problems in the series. So that's really, it's way out there. We're nowhere near being able to make an android, but that's really what we're thinking of, is this partnership that we're trying to build between humans and machines. So how are we going to really get from where we have been in the programmable systems era to this cognitive systems era? Well, the reason I brought up Lieutenant Commander Data is that, frankly, the makers of Star Trek were right. What gets you across that gap is the availability of data. And we've all heard a lot about big data. I won't go through all the different, you can go into almost any news article and find another sound bite on how much data there is. What I prefer to think about is not so much the volumes of data, which are enabling, but the very diverse types of data. There's data about almost every subject on Earth. There's data about almost every phenomenon on Earth. There's data about things out in space. I don't know why I'm saying on Earth, right? There's data about almost anything. Comes in very diverse shapes and forms. And frankly, the biggest problem we have with all this data today is that it's actually very hard to get anything valuable out of it. We're really drowning in data. And so the thesis of the next part of my talk really is that cognitive systems, just as data enables the machines to learn, which allows us to do cool cognitive things, it's that cognitive technology that is helping us get value out of all the data that's out there. So they're symbiotic, the cognitive and the data systems. So what I'm going to do in the rest of the talk, we have fairly limited time. I'm going to try to talk briefly about each of three very cool, I think, capabilities that we're trying to give the computer systems. and try and give you a sense of both the data that is driving that, but also the variety of that data, and then the very sophisticated types of analytics that are needed to make those leaps. So I'm going to start with what I really thought when it was first proposed to me was going to be totally science fiction. The ability to have a computer that could be a real research assistant to a trained medical researcher, a good medical researcher, and help them build hypotheses and decide what the next experiments they should run would be. This was proposed to me by Dr. Olivier Lichtarge at Baylor College of Medicine shortly after Watson burst on the scene with this great win in Jeopardy. He said, look, you've got a computer system that can read large amounts of information. I have a huge problem. The medical literature has been exploding for years. I'm a cancer researcher. There are 70,000 articles on just one gene known to be implicated in cancer in my field. Now, if you do the math, you would realize there is no such thing as a medical researcher who could have read all 70,000 papers in his lifetime. In case I wasn't impressed enough and worried enough, he told me that people are writing about 5,000 new papers in the field every year. So just think about how many papers you'd have to read a year. You can't do it. So I said, okay, yes, we could probably build enough knowledge into the system that it could read these papers and maybe build a model of its understanding, but how do you think it's going to help you to have that? He said, well, what I want it to do is to make some hypotheses for me and tell me what experiments to do. So I'm going to tell you very briefly what the first problem we agreed to tackle together was. He had taken, he was very interested in this one gene, P53. P53 is known to medical science as the cell's angel of death. So a healthy cell is born, it goes through a lifespan, and it dies. When cells don't die, bad things happen to our bodies in various ways. If they die too soon, bad things happen too. So it turns out this P53 is the gene that regulates what the life cycle of a cell looks like. And about 50% of all cancers, P53 is not working quite correctly. Now, science has also known for quite a while that there's a class of proteins called kinases that can help regulate P53. But they don't all work under all circumstances, and so people are very interested in finding new kinases. There's a lot more articles on kinases, it turns out, than there even are on P53, but ignoring that for now. This was the problem that Olivier wanted us to help with. He said, look, we're finding one new kinase a year. That's too slow. We're not finding the ones we need. I want a system that could tell me where the best places are to go looking for kinases. And I'm betting that in 70,000 papers in the literature, there have got to be some hints that I'm just not seeing, some dots that could be connected. And if I could connect those dots, maybe I'd know where we ought to go. So I was dubious, but we said, fine, we'll do that. We took Watson. We had already been teaching it a lot about chemistry and drugs and other sorts of things. Now we started adding some very, very basic biology, mostly very focused on this one piece of the problem, so around genes, kinases, P53 in particular, and a few kinds of connections, phosphorylation and other sorts of things, if you're technical in this field. I'm not. We got it going. We fed it a bunch of medical abstracts from the literature and trained it on those. And then we decided to do a test. And we decided to do a retrospective test. So we gave it all of the medical abstracts from the whole Medline literature from the beginning of that repository up through the end of 2003. This was 2014, basically, that we were doing this work. And we fed all that into the system, had it read those papers, and then we said, tell us what other kinases you think there are. So just predict forward. And we gave it some very simple tools for doing prediction, very, very simple tools. At that point in time, mostly linguistically based. And so we ran that prediction, this funny colored graph here. It says there's a laser pointer. These colored nodes represent, the green represent the known kinases as of the end of 2003. The other colors represent predictions from the system, colored somewhat by the heat tells you how strong a prediction it was, although orange and red are about the same. So the yellow it wasn't quite so sure about, but it really liked these orange and these two red nodes as candidates. So then we went and we looked at the literature from 2004 through 2014. All those orange ones had been found in that time. The computer had correctly guessed that, in fact, these seven proteins were kinases. But what about the two red ones? What was wrong with those? Why had it said those two with such certainty? Well, our colleagues couldn't find anything in the literature about those two, so they went off and tried to do some experimentation in the lab. And it takes a long time to run these experiments in biology, and that's one of the reasons he was so interested in being pointed in a good direction. About a year later, we had proof that from both in vivo and in vitro experimentation that these two were kinases. So our system had discovered two new kinases out of this. So a lot more work to do. I'm not claiming that we have the new medical researcher. It has to be a very well-formed problem and so on, but it is really exciting. It was very exciting to our colleagues in Baylor to think that they might have a tool that could help them choose the right experiments to do and allow them, therefore, to get better much faster. So that's an example. I want to switch gears now and talk about a different kind of data, a different type of problem altogether, but another one in which we're trying to train a computer to be a helper and assistant, and it's also in the medical space. I promised to do one not in the medical space, but this one is. So this is about having a computer help a radiologist. What's the radiologist's problem? A good radiologist looks at medical images. They'll look at hundreds of studies a day, often with hundreds of images each. They can easily do, I think it was tens of studies a day. Humans are a little more limited than that. They can easily, though, be looking at thousands of pictures a day. And of those pictures, they're usually looking for what's wrong, what's the problem with this individual. Very few of those pictures will tend to show the problem. It's like looking for needles in a haystack. So the question is, could you train a computer to recognize images and to find the anomalies in those images, to find those and to highlight them for the radiologist, so the radiologist, instead of having his eyes glazed over by his or her, I have a daughter-in-law in this space, so I better be careful, instead of their eyes glazing over, from looking at so many images, most of which aren't showing things, with the risk of eye strain, with the risks of actually missing the actual problems, could you just highlight for them exactly the images that they need to look at and are where they're most likely to find the problem? This turns out to be quite a challenge, as you can sort of see from the little images up there. These things look a lot alike. I know you're seeing them very small. The radiologist would see them much bigger, but they don't differ a lot from image to image. And depending on what we call the modality, the type of imaging that you're doing, or the part of the anatomy that you're looking at, there are very different things that you would look for as signals of something being wrong. So the the way you look for things in the heart, for example, is very different than the way you look for a bone break or something like that. They're different sorts of signals that you need to look at. So it turns out, in order to tackle this problem, you need a lot more than just some machine vision. We end up being able to take advantages of the images, of course, but have to be able to feed that computer the full knowledge that the radiologist or a doctor would have as well. They need the clinical history of the patient. They need knowledge of the diseases. They need reports with lab tests and so on. All of that has to come together to enable this system to actually be able to filter out the images that have the most meaningful that show best what's going on with that patient. And so you see at the bottom there's a lot of cognitive technologies, the ability to read and understand text, the ability to read and understand images, the ability to learn. What enables the leaps forward that we're making here is the fact that we have so many radiological images online now, and so we can actually start to really learn from what other radiologists have looked at in the past and what they have found in those images, and so on. So that's a second very different kind of project, again, on a very different sorts of data, but where the technologies and the data play a really strong role. So I promised a non-medical example. And so let me take one that may feel a little closer to most of us. And this is something we call cognitive debating technologies. Today, if you go online and you're trying to make a decision, a lot of times we do things like we search for information, and the computer's gotten really good at finding us things that might be good for us to read or to know about or to think about as we try to make our decision. But what it can't do for you is really give you an argument, show you what are the pros for going one way and the cons for going another. That's a very hard problem today. And so what we asked was, where can we go to make the computer more useful to people who are really in positions of having to make decisions, ranging from relatively simple things, should I buy a house or rent, which of course varies depending on hundreds of variables, and you get tools, all of which have different points of view and give you different answers online and so on. But something we all probably face at some point in our lives, to really big business questions. I'm IBM. Do I partner with this company over here? Do I want to acquire this company, or should I just compete with this company, right? So those are decisions that our business people make every day as they look at the field around them and so on. There are no right or wrong answers. How are you going to address that? Well, our researchers thought this is sort of like the skills you need in a debate. What do you do if you're a debater in, say, high school or college, or not presidential debates, okay? The U.S., especially not the U.S. presidential debates. But let's take real debaters. Real debaters go out and they do research, and they have to be able to defend both the pro or the against, I didn't say that right. Anyway, they have to be able to defend both sides of the argument. So they have to go out, they have to find relevant information, and so they would do that by doing some searches and so on in the web ahead of time. They have to organize it. They have to figure out an argument, what an argument is. An argument consists usually of a statement, a topic statement, a set of claims that would tend to support that argument, and then evidence for each of those claims. So they have to find the claims that that come out of the news articles. Then they have to find evidence for each of those claims, which might come from way different sources. And then they would have to put them together into a reasoned argument, right? And so that sounds a lot like what you need as support for a decision-making process. So our researchers said, let's see if we can teach a computer to do that. And that's why they call it debating technologies. Now, this is a very hard problem in general, and I'm not going to have time to explain to you all the different pieces of it, but I did want to just have give you a little sense of why this is so hard. And so to do that, first, a little bit of background. Even if you restrict your data sources to Wikipedia, and actually we use Wikipedia and news sources and a whole bunch of other things, and just look at that, you end up with a lot of different possible claims coming out of all the sentences and all the articles in that database. So you could think of trying to figure out what the claims are if you had to do brute search as finding a needle in a haystack, really. A lot of different candidate claims that would be good, but how do you find the right ones? Actually, it's worse than that, and that's what I want to show you now. We're going to do a little game. We're going to give you a real example. So at the top, I have a topic statement for the argument that we want to make. And the topic is that the sale of violent video games to minors should be banned. Now, what I'm going to do is show you some other statements, and you're going to vote as to whether that's a claim or not. You can raise your hands if you think it's a claim, okay? So, violent video games should not be sold to children. Is that a claim? You saw one hand. Now, either this is a very smart or a very shy crowd. No, it's not. It's just repeating the topic, so it wouldn't help your argument, right? A claim should advance the argument. How about this one? Violent video games are significantly associated with increased aggressive behavior. Does that advance an argument? Yes, it does. So that's a claim. We would call it a factual claim because you would expect your evidence for that to be facts. You would be able to find facts or studies or things that you could bring forward as evidence. Here's another one. Doom, that's a game, for those of you who don't know American game culture. It has been blamed for school shootings. Some yes, some no. The no's are correct. That's too specific. It doesn't help me make a general case or a strong argument for this. How about only children predisposed to aggression are affected by violent video games? Number of people think that's a claim. No, that's ambivalent. It could be used in either direction, right? Maybe it's only a very small subset of children, so that's not a strong argument as to why you should ban sales, right? But it could also go the other way. Maybe all children are predisposed to aggression, and therefore it should be an argument for. So it's not really a strong one. TV shows just mirror the violence that goes on in the real world. It's a true statement, perhaps, but it's not a claim because it's not relevant to violent video games. Doesn't tell us about that. So what I'm trying to do here is show you that it's not just a matter of finding a sentence that has something to do with the topic. It's really subtle which things can go together into an argument. Got two more, I think, here. Video game publishers unethically train children in the use of weapons. Is that a claim? Yes, it is, actually. It's an opinion, but it is a claim, and you would expect to find evidence for that in other, educated people's opinions, great speakers, great philosophers, and so on. And finally, video game addiction is excessive or compulsive use that interferes with daily life. No, it's just a definition, yeah. Okay, so again, point is, these things we're asking the computers to do these days are challenging even for us. Even with all the education that you've had that landed you in a room like this talking about technologies and so on, these are hard problems. We're making good progress on this. We actually do have a system that does basically as good a job of identifying claims as most humans do, even trained debater type humans. And we are now working on some of the pieces of putting these things together into logical arguments. And again, the hope is that over time, it's not just a game to debate, it's about helping people really solve real problems and make real life decisions. So I'll wrap up here. I'd like to welcome you to the cognitive era. If you look at the history of mankind, you can see it as constantly overcoming certain kinds of limitations. We did physical limitations. We had limitations in terms of how we were connected to each other. We had limitations in terms of how much one individual could do in a day, productivity limitations. And we have had complexity limitations. How much can one human being cope with? It used to be only what your brain could do. We now have these very cool emerging assistive technologies, and who knows, maybe in the future we'll have lieutenant commander data. Wherever we end up in this quest, I really believe that it's data and cognitive computing together that are going to allow us to tackle a lot of the big problems that are essential to our future. You could go on listing problems forever that there is interesting data about and room for really impressive advances in cognitive reasoning to help us solve them. So I'd like to thank you for our time and attention. I have to thank the ACM who sponsored my being there.